Hi friends, welcome back to my channel. Today in this video we are going to look at the details regarding harmonic analysis of a 2 degree of freedom system. So here I have shown a 2 degree of freedom system. So first we will see the closed form solutions, then we will go to a commercial software package, finite element software package called ANSYS. Then we will see how we can carry out or solve the same problem in ANSYS and then compare the results from closed form solutions as well as from ANSYS. So before we move ahead, what I have shown over here is a 1 degree of freedom system. It is 1 degree of freedom system because the whole system configuration can be explained if we know the displacement of this node 2. Unlike that situation, here things are a little different. Here we have two masses, so I should know the displacement of m1 as well as m2. Then only I can completely define the system. So that's why this classifies as a 2 degree of freedom system, while this classifies as a 1 degree of freedom system. In the last video we looked in detail how to solve this particular response using closed form solution and how to solve the same in ANSYS. So in this video we are going to look at a 2 degree of freedom system as shown over here, like this. Or this is one displacement felt by this particular mass m1, and this x2 is the displacement felt by the mass m2. To be pretty precise, x1 is actually an x1 function of time, and x2 also similarly it's a function of time, x2 of t. I may not be explicitly writing this out, but please keep in mind that when I simply tell x1, it's a function which varies with respect to time. Okay, now we need to arrive or derive the equations of motion for the system. It's not that difficult, but a little bit of common sense is required here. So what I am thinking over here is that, okay, let's say x2 is greater than x1, then the spring k2 will be subjected to tension like this, and the force in the spring will be k2 into x2 minus x1, where x2 minus x1 is the relative elongation in the spring. So if this middle spring is in tension, that means the m1 will be acted upon this side by a force like this, and m2 will be acted upon by the same magnitude of the force but in this direction, Newton's third law. Now coming to the mass m1, as it moves towards the right, as it tries to move towards the right, the k1 spring, the spring with stiffness k1, will try to pull it back. So that's why this force k1 x1 is acting on m1. Similarly here, what happens when the m2 mass starts trying to move towards the right, it will be pushed by a force k3 x2. So that's what is shown over here. Now the next step is to write equations of motion for the same. Let's start out writing equations of motion for the first mass. So the first mass is acted upon by three forces, and this is the positive direction of x1, function of t. So the acceleration will be x1 double dot t is referred to as d square by dt square of x1 of t. So mass times acceleration, simple Newton's third law, is equal to, we have to sum up the forces in the algebraic sense, or the by giving respect to their sign. So k2 into x2 minus x1 is acting along the direction of x1 double dot t. So I'm putting a positive sign over here. Minus k1 x1 is acting in the opposite direction. That explains the negative sign. Again, f1 of t, the external force acting on the mass, that is again along the direction of the acceleration. So that's how you end up with this expression for the first mass. Now let's move to the second mass. So here also the second mass, if there is any external force, this is the external force acting on mass 2, then this is the force coming from the third spring, and this is the force coming from the second spring. So then writing out the equations with the conventions whatever we have explained before, we get this equation. Now let us have a close look at these two equations. So these two equations, one thing is pretty sure, they are connected, they are not independent, they are dependent. If you see, x1 is dependent on x2, similarly x2 is having again a dependence on x1. So these two are simultaneous equations, what we call in a strictly mathematical sense, what we will call them is coupled. The system is two coupled second order differential equations. Let's not bother about those things too much. Then similarly, this two equations can be written like this also in a matrix form. It's far more concise that way. So mx, this is a matrix and this is a vector, or a raw vector you can call. Then the same thing can be written in a matrix form also. This makes our computations fairly easier. So let's summarize. So we had a look at a 2 degree of freedom system. Then we wrote out the differential equations, or the equations that govern the motion of these things. Then we came to realize that there are two coupled second order differential equations. Now let us see how we can solve them. Essentially, these two are differential equations. I hope you remember basic concepts in solving a differential equation. We have both general solution as well as particular integral. So general solution is the solution when you have the right hand side equal to 0. Physically, what does that mean? Physically, in a vibration problem, that means we are looking for a solution in the system when there is no external forces acting on it. Let me clarify a little bit more. Let us try to get some physical intuition to this whole thing. So, what I am telling is that let's say I am giving an initial disturbance to the system. For example, I am pulling the mass m1 towards the right side by, let's say, 2 mm, and then leaving the system. Then are there any frequencies with which the system will oscillate? Because once you give an initial disturbance, you are leaving the system as such, or in other words, mathematically, there are no excitation forces acting on the system. The right hand side is 0. So you are looking at whether there are any particular shapes or frequencies with which they will vibrate once you give an initial excitation and then leave the system. That's what exactly you are looking at when you say you are looking at the uh, general solution for a differential equation. So in this case, I have shown two shapes. Like let's say I apply unit displacement to both these masses m1 and m2 and then leave the system. Then there is a particular way the whole system behaves. There is a particular frequency with which both these masses move. And let's say next time what I'm doing is I'm still pushing the m1 towards the right, but m2 this time I'm pushing towards the left. So that means I'm giving a initial displacement like this to m1 and like this to m2. Then is there any mode, or is there any shape the system will assume, like as shown over here? Then what are these two frequencies? That's what we are looking at essentially when we are solving for the general solution of this equation. Make sense? So let's say my x1 is capital X1 e raised to I omega t, and little x2 is capital X2 e raised to I omega t. Please remember this x1 contains phase information. For the time being, let's assume that and this x2 also contains phase information. Then these two are unknown frequencies. We don't know what are the probable frequencies that may come out of the system. That's what we are interested in. So we are assuming that when you have a particular motion, both will be excited by I mean they are moving at the same frequencies. That's why the omegas are the same. Like you can't have one frequency for here and you can't have another frequency here. When they vibrate together in a mode, they both have the same frequencies. So now with that assumption, go ahead and see how the equations slightly take a change. Now this was the system of equations what we had. Definitely the right hand side is going to be 0 because we are looking the solution for a free vibration problem, or in a mathematical sense we are looking for the general solution. Then definitely I can I can differentiate little x1 twice to get these two things. Then I'm plugging in all these things here. Once I plug in this, I will get this. Again, doing some mathematical operations, very simple mathematical operations. In fact, this omega square can be brought here, minus omega square can be brought inside here, because I need to have x1 stand this particular column vector to come out of this equation like this. Then once these two are common, I can club these two matrices and I am here. Now I'm looking for what is the x1 and x2. See, one obvious solution is that x1 and x2, assuming zero values, always will satisfy the set of equation. But that's not something what we are looking at, because that's a trivial solution. We are looking for a non-trivial solution to a system of homogeneous equations. So this is a system of homogeneous equations. Why? Because the right hand side is 0. And trivial solution, we all know x1 assuming a value of 0 and x2 assuming a value of 0. We are looking for a non-trivial solution. So for this system of equations to have a non-trivial solution, this particular determinant should be 0. So in general form, we can write it like this. Determinant of the K is the stiffness matrix, M is the mass matrix, omega square is the frequencies that we are looking for. Then this boils down to this equation where it is an omega to the power of 4, or there can be two possible values for omega square. Why? Because it's a quadratic in omega square. So omega square will have two possible values, omega 1 square and omega 2 square. So we find that physically what does that mean? So there are two frequencies, omega 1 and omega 2, with which it can vibrate when you give a certain type of initial excitations. There are two natural frequencies for the system. Now, once we know that this equation, this equation is satisfied for two omega 1s, then what we can have, we can write, or we can find the ratio of x1 and x2 for each of these, isn't it? Like if we plug in omega 1 here, we will get a ratio of x2 to x1 corresponding to omega 1 from this equation. Similarly, we will get, and it has to be the same, whatever, once we plug in omega 1 square here, we will get again an x2 and x1 ratio, x2 by x1 ratio. So what I mean trying to say over here is that we can define an R1 corresponding to the first frequency. Then what will be the resulting displacement? It will be x1 times R1 x1. So let's say if the right hand side moves by 1 unit, the second mass moves by R1 units, R1 into 1, R1 units corresponding to natural frequency 1. And how you evaluate x2 by x2 1 by x1 of 1? All you have to do is plug in omega 1 square in this equation. Similarly, corresponding to omega 2 also, we can have a ratio of displacements. Here I am putting 2 to drive home the point that this is corresponding to the second natural frequency, not the first natural frequency. This is corresponding to the first natural frequency. So this is the ratio or the displacement vector. I shouldn't have wrote x2. It is simply x vector, again the displacement vector, but this time corresponding to the mode or the natural frequency 2. Now these ratios, they are called the mode shapes. Okay, very important. So there are two natural frequencies and there are two mode shapes, or two ways in which these things can vibrate in the free vibration problem. So let's summarize this video. We were looking at a 2 degree of freedom system. We were trying to solve the forced vibration problem where we had continuous forces acting on the two masses. Then we told that no, before we solve for the complete system, first we would like to see what is a general solution for the system by forcing the right hand to be 0. In other words, you leave the system after an initial excitations. Are there certain possible frequencies with which the system may oscillate, and if it oscillates, what will be the shape? So these are the two natural frequencies, and these two are the corresponding mode shapes. So whatever I have shown earlier, these two are called the mode shapes. Why it is a mode shape? Here, if we write the displacement vector, it will be, if this mass is moving by one amount, the same amount the mass 2 also moves. If this mass m1 moves 1 mm, here it also moves 1 mm. So the mode shape corresponding to that will be 1 1. While the mode shape corresponding to this will be, you see here, this mouse moves 1 mm towards here, this one moves in the opposite direction. So here the mode shape will be something like this, 1 minus 1, and these two may be corresponding to one natural frequency omega 1 and omega 2. So these are some basic idea of what are natural frequencies and what are mode shapes. So I hope you understood the concept of natural frequencies and the mode shapes. In the next video, we will try to solve the system of equations.